Hello everyone, welcome to the lecture again. In the context of the dynamics of rigid bodies, in the last few lectures we have discussed the fixed axis rotation, general plane motion, work energy equation and impulse momentum equation. Today we are going to discuss the angular momentum of the rigid body. Let us say capital XYZ are some fixed reference axis and then we have a rigid body, and with this rigid body we attach a small XYZ okay. So, capital X, Y and Z, these are the fixed reference axis, and note that this rigid body is making a general plane motion. So, a small x, y, z, these are the axes that are attached to the body, and let us say their origin is at the mass center of the rigid body. Okay. So, this is G. Okay. Now, if we observed from the capital XYZ reference frame, and let us say this rigid body is having a angular velocity omega, in that case a small xyz axis will also rotate with the same angular velocity omega, because these axes are fixed with the rigid body. So, let me mention this point, that as observed from the fixed reference axis, that means capital XYZ, the angular velocity omega of the body, it becomes the angular velocity of the small xyz axis, because small xyz axis are fixed with the body. So, we are saying that let us say this rigid body is having a angular velocity omega, and this also has a linear velocity, let us say v. So, what is the angular momentum about the mass center G? Well, the angular momentum about mass center G will be Lg, that is equal to the sum of moments of momentum about G. Okay. And to find out the sum of the moment of momentum, let us say I have let us say ith particles, its mass is mi, and let us say its distance from G is rho I. Okay. So, Lg will be, so there are n particles, let us say, so sum over I, rho I, okay, this is the moment multiplied by the momentum mi vi. Okay. And since v is equal to omega cross r, here r is rho I, so therefore this can be written as sum over I rho I cross mi omega into rho I. Note that omega is independent of I, because the body is rotating about G. Okay. So, therefore, Lg will be integral. So, I can write down summation into integral rho into omega cross rho and dm. Let us call it equation number 1. Now, suppose instead of rotating about g, let us say the body is making a fixed axis rotation. So, the same scenario, I have this rigid body and let us say this rigid body is making a fixed axis rotation about O. Then again we have capital X, Y and Z. Axis, and then we have small x, y, z which are fixed with the body. So, when the body rotates, the small x, y, z axis will also rotate. So, let us say this is small x axis, small y axis and small z axis. Let us say the mass of the ith particle is mi and its distance from O is ri. So, as I said, small x, y, z axis, they are attached to the body. Okay. Therefore, both body and a small x, y, z axis, they has angular velocity omega. Now, in this case, what is the angular momentum about O? Well, again it is moment of momentum. So, sum over I Ri cross Mi Vi, and Vi is omega cross R. So, I can write down sum over I Ri cross Mi omega I cross Ri. And of course, this I can write down in the integral form. So, this is r cross omega cross r dm. Let us call it equation number 2, and you can see that equation number 2 and equation number 1, they have the identical form. So, in equation number 1, we calculated the angular momentum about the mass center g, and in equation number 2, we calculated the angular momentum about a fixed point O. Okay. So, equation number 1 and 2, they have identical forms. Okay. And I can also write down this equation as L about O or L about G is equal to integral dl. So, in this case this dl becomes r cross omega cross r into dm. Okay. Now, to find out what is this quantity, let us write down component by component. Okay. So, r cross omega cross r into dm, we are interested in finding out this quantity, so that we can find out what is LO or LG. So, this I can write down as, so r is xi plus yj plus zk in the Cartesian coordinate. So, this is xi plus yj plus zk cross, then we have omega, omega also has xyz component. So, omega xi plus omega yj plus omega zk, and cross product with again r is xi plus yj plus zk, and then we have dm. Okay. So, first let us calculate this cross product, and that is equal to xi plus yj plus zk cross product I j k omega x omega y omega z x y z, and then we have to multiply it by dm. So, this becomes xi plus yj plus zk cross product. So, we have I omega y z minus y omega z minus j omega x z minus x omega z plus k omega x y minus y omega y, and then you have to multiply it by dm. Now again this is a cross product of two vectors. So a cross b, again we can write down in the matrix form, and we can evaluate its value. So this becomes I, j and k, and we have x y z, and then we have coefficient of I, j and k. So the first one is omega y z minus y omega z, and then the coefficient of y is minus omega x z minus x omega z. So this I can write down as x omega z minus omega x z, and then the coefficient of k, which is omega x y minus x omega y, and then we have dm. So let us calculate this also. So this becomes I y omega x y minus omega y x minus z x omega z minus omega x z into dm minus j x omega x y minus omega y x minus z omega y z minus y omega z dm plus k x into x omega z minus omega x z minus y omega y z minus y omega z into dm. Now we can collect the coefficient of omega x and omega y and omega z inside I, j and k. So here I have omega x, omega y and omega z. Let us collect their coefficient. So this I can write down as I. We have y square plus z square into omega x minus xy omega y minus xz omega z dm plus j minus yx omega x plus x square plus z square omega y minus yz omega z dm plus k cap minus zx omega x minus zy omega y plus x square plus y square omega z dm. Okay. So now we have the value of r cross omega cross r, and we can put that value in equation number 2 or equation number 1. So we have to just take the integral of that. So L will be integral I y square plus z square omega x minus xy omega y minus xz omega z dm plus integral j minus yx omega x plus x square plus z square omega y minus yz omega z dm plus k integral minus zx omega x minus zy omega y plus x square plus y square omega z dm. Okay. Now note that this omega x, omega y and omega z, they are independent of the ith particle because the body is making a fixed axis rotation. So therefore they can be taken outside the integral. Okay. Now another important point is, look at this quantity y square plus z square dm. Okay. Similarly xy dm and xz dm. So you have to recall that integral y square plus z square dm is the moment of inertia about the x axis. Okay. So this is I xx. Similarly z square plus x square dm is the moment of inertia about the y axis, and integral x square plus y square dm is the moment of inertia about the z axis. Similarly, integral xy dm is the product of inertia about the xy axis, and integral xz dm is the product of inertia about xz axis, and integral yz dm is the product of inertia about the yz axis. Okay. So, let us put that in the above equation, keeping in mind that omega x, omega y and omega z are independent of the integral. So, we have L equal to I xx omega x minus I xy omega y minus I xz omega z into I. This is the first term, because this becomes I xx. So, we have I xx omega x minus I xy dm, integral becomes I xy. So, that is the second term, and then you have omega y, similarly I xz omega z, plus minus I yx omega x plus I yy omega y minus I yz omega z j plus minus I zx omega x minus I zy omega y plus I zz omega z k cap. Okay. So, these are the component of the angular momentum along the I axis, along the j axis and along the k axis or unit vectors. Okay. This I can very nicely write down in the matrix form. So, Lx, Ly and Lz, it can be written as I xx minus I xy minus I xz minus I yx, I yy minus I yz minus I zx minus I zy, I zz and omega x, omega y and omega z. Okay. And note that this matrix over here is what? This is the inertia matrix that we introduced when we discussed the moment of inertia and product of inertia part. So, this is the inertia matrix, or you also call it inertia tensor. Okay. And therefore, I can write down this in more compact form. L is equal to I omega. Okay. Here this I is the inertia tensor. Now, you have to note that as we change the orientation of the axis small x y z, then the moment and product of inertia also changes, because we have fixed them with the rigid body. So, relative to the body, then the moments and products of inertia will also change. Okay. And we have also discussed that you will always find unique orientation of the body or of the small x y z axis, for which the product of inertia will vanish, and this is called the principal axis. So, this also we know that there is one unique orientation of small x y z axis for which the product of inertia Venice, okay, and this is called the principal axis. Okay. So, in that case the inertia tensor will be Ixx, Iyy, Izz, and all the product of inertia, they will be 0. Now, if that happens, in that case the total angular momentum L will be Ixx omega xi plus Iyy omega yj plus Izz omega zk. Okay. Therefore, in this case your Lx, Ly and Lz, they becomes Ixx, Iyy, Izz, and the product of inertias are 0 into omega x, omega y, omega z, and this tells you that if the coordinate small x y z, they coincide with the principal axis of inertia, then the angular momentum about the mass center G or about a fixed point O will be L equal to, so let us multiply that, we have Ixx omega xi plus Iyy omega yj plus Izz omega z k. Okay. Now, we have also shown that for general plane motion, okay, and this is something that we proved, that the kinetic energy T is equal to half m v square plus half I omega square, where this I bar is the moment of inertia about the mass center and v bar is the linear velocity of the mass center. Now, for fixed axis rotation, there is no v, so half mv square term will not be there. So, therefore, T becomes half I omega square, and just now we have seen that L is equal to I omega, therefore, I can write down kinetic energy T equal to half omega LO or LG. Okay. With this introduction, now let us look at an example, and the problem statement is following. The bent plate has mass of 70 kg per square meter of surface area and revolves about the z axis at the rate omega equal to 30 radian per second. Determine A, the angular momentum L of the plate about point O and B the kinetic energy T of the plate, and it is given that neglect the mass of the hub and the thickness of the plate compared with its surface dimensions. Okay. So, in this question we have been asked to find out the angular momentum L of the plate about the point O. So, about point O, this is making a fixed axis rotation, and first we have to find out what is the inertia matrix. Okay. So, the inertia matrix I am not calculating because this is something that we have done earlier. Let me write down the final answer for the moment of inertia matrix for this geometry. The dimensions are given and I comes out to be 0.0257 minus 0.00369 minus 0.00221 minus 0.00369 0.0130 minus 0.01012 minus 0.00221 minus 0.01012 and 0.01834. Okay. So, note that this is the moment of inertias about the x, y and z axis, and these are the rest of them are the product of inertias. Okay. Now, in this question it is given that omega z or the angular velocity about the z axis is 30 radian per second, and there is no rotation about x and y axis. So, therefore, omega x and omega y will be 0. Now, the angular momentum about the x, y and z axis we have already find out. So, this is the angular momentum about the x axis, this one is the angular momentum about the y axis, and this one is the angular momentum about the z axis. So, let me just write it down. The angular momentum about the x axis is I xx omega x minus I x y omega y minus I x z omega z. Ly is minus I y x omega x plus I y y omega y minus I y z omega z, and Lz is minus I z x omega x minus I z y omega y plus I z z omega z. Okay. Now, the values of omega z, omega x and omega y is known, and also the moment of inertia and the product of inertia. So, we can put the values. So, Lx comes out to be 30 into minus 0.00221, because omega x and omega y is 0. So, this term will not be there, that term will not be there. We have only I x z and omega z, okay, and I x z is 0.00221. Okay. So, let me just write down, this was your I x x, this was I y y, this was I z z, and this was minus I x y minus I x z and so on. Okay. So, similarly, Ly will be 30 into minus 0.01012 and Lz will be 30 into 0.01834. Therefore, the angular momentum about point O will be 30 minus 0.00221 I minus 0.01012 J plus 0.01834 K Newton meter second. Okay. Now, let us find out the kinetic energy T of the plate. So, since this plate is making a fixed axis rotation, so therefore, kinetic energy T will be half omega into L naught, and L naught we have find out, omega is also known, this is 30 K cap. So, it will be half 30 K cap dot L O, and L O is here. So, this comes out to be 8.250. With this, let me stop here. See you in the next class. Thank you.